Basically, you've got 4 new derivation rules to learn. There'll be one more thing next week. And I suspect you can guess what the derivation rules are. We've got to have both elimination and introduction rules for the universal quantifier and for the existential quantifier. And what I'm going to do at first is just work through the first 2, because they're extremely intuitive, simple, and they should cause you no trouble at all. The second 2 are less intuitive, at least, if not sometimes bewildering, but they're a little less intuitive. Once you get the swing of it, both the universal introduction and the existential elimination, I don't think you'll have any trouble, but there's these little tricky provisos. You're allowed to do it under some circumstances, and those we'll have to go over a little bit more carefully. But at first, best way to do this, I think, is just to plunge right in. So rather than doing a lot of rigmarole, what I'd like you to work with you on is first, I'll be doing this up here, but look at this particular problem. You're given on each line a what it is you're supposed to do. You're supposed to apply universal elimination to line 2 to get line 3. But we'll talk our way through this, and we'll begin to understand how both these first 2 things work. So first of all, what would you guess I'd want to do, Mike, in line 3 in order to apply universal elimination to line 2. On line 2, we have a universal quantifier, all x, bx. What might be a reasonable candidate for line 3 using universal elimination on line 2? What might I write down? Talk it through if you want. I mean,
bx or something. Oh.
B something. Well, what we're doing is getting rid of a quantifier. It says, and the quantifier quantifies over variables. So it's saying for all x, for everything in the universe. What line 2 tells us, for everything in the universe, because we're given no universe of discourse. So we have to figure it's everything. So given that the universe covers everything that could possibly be in the universe, it says everything has the property B. Everything is a B. And that's what line 2 says, right? It says for all x in the entire universe, bx. X is a B, or has B, or whatever B stands for. So now I want to get rid of the universal quantifier. I want to conclude something from that. So since I know that for all x, bx, and I want to eliminate the universal quantifier, is there anyone who can help out by suggesting what we might want to do down here on line 3? Pardon? Not just B, because B just says something like has boots. Anybody else have a suggestion? Pardon? We do need a name. So what would you write down here on line 3? B small a, right. You can pick any name in the entire lexicon of possible names, because line 2 says everything has property B. So now we're going to say, all right, well, then if we know that in particular, eliminating the universal quantifier, A, for example, is a B. So is B, so is C, so is D, so is E, so is F. Everything is a B. But we know that A, B, A, all right? And we could have chosen any letter we like. And what we'll find out in the course of derivations is which letter you choose matters a lot when you're dealing with mixed quantifiers especially, or if you're in a situation where you're already given something with a name in it. Because then if you have something else that universally quantifies over the entire domain, then it also then that property also is held by A, B, C, everything in particular in the domain, and that can be very helpful in derivations in the future. But for now, let's just look at what we've done. We've taken as an example that since everything is B, that's what line 2 says, we know that in particular A is. So that's what we did in line 3. Now let's do the same thing with 1, and that shouldn't be very difficult at all. Will Stanton. Do the same trick with 1 using universal elimination on line 1. What would you get?
You should just get A of something and not C of something. Like
Yes, but pick a something.
B.
Okay, you can pick anything you want.
So you get AB and not CB.
Ampersand, not C, B. Because that's universally quantified, so you can pick any letter. You could have picked A. And that's something you can't do in other situations with some of these other rules, like in particular, existential introduction. You can't just willy-nilly use something you've already used. You have to be very cautious about that. I'm sorry, existential elimination. All right, so that's a good candidate for line 4. And now what we want to do is we haven't even given you the rule, but we want to see what happens. I want to try to figure out the logic of existential instantiation. So now we'd like to operate on BA, that's line 3. We want to operate on that using the rule existential instantiation. Nathan.
EX, BX.
So we're introducing an existential quantifier, and yes, that works fine. And now what is this? What's the logic of this? Well, once again here, the logic indicates that, well, look, if you know this, and every time you have something in the main derivation, if you have something in a line in the main derivation, you might as well say, all right, if I know that, then what? What can I conclude? And similarly, within the subderivation, but then you're going to have to be careful about not pulling out some of the assumptions there into this line. But wherever you've got a derivation, you can say, all right, if I know that BA, if I know that A has the property B, if I know A B's or has B or whatever it is, well then I know that there exists at least one thing in the universe of discourse that has that. In particular, it's A. So I'm entitled from line 3 to introduce an existential quantifier. I couldn't, on the basis of line 3, legitimately introduce a universal quantifier. I can't, because if I didn't have any of this, if I only had line 3, there'd be no reason in the world for me to think that just because A has the property B that everything does. So I cannot introduce a universal quantifier that way. I can introduce an existential quantifier that way, because all EX, BX says is there exists at least one, maybe more, but there exists at least one thing in our universe that B's, and we know that because we know that A does. All right? So that's how we get line 5. Now let's just do this simply. It doesn't matter which one we take out. Let's take something out of 4 using good old ampersand elimination, and I'll do that myself. Let's take out AB. Is that the one we wanted? 3, 6. Yeah, and then finally we'll take 3 and 6 by ampersand introduction, and that gives us BA and AB. Okay? And then finally, let's see, Brad, tell us what we should do at line 7, or line 8. We're going to operate on line 7 using existential introduction. We did the same thing operating on line 3 at 5, so basically, what would we do at line 8?
There exists an X such that BX and AX?
Yes.
Those aren't the same numbers, right? Or names. So changing out to
I'm sorry, Max?
those aren't the same names.
What names?
You have BA
A?
and AB. You have A and B.
Oh, I'm sorry, that's right. I can't do that, can I? So maybe what I should have brought down was, in order to perform the move that you see, what Max is pointing out is I've got different names. So all I could separate these out or they were already separated out. I could go back to, as I did in line 5, I could say EX, BX, and then with line 6 I could say EX, AX, but I can't from line 7 directly do that because I've got different names there. It's not this, what this would say, what your suggestion was, this would say, it's the same thing. It's the same x. There's at least one x that both has the property B and the property A. We're not entitled to say that from 7. We're saying one thing has the property B and another thing has the property A. So we're not entitled to draw that conclusion at 8. Do you see that, Brad?
Yeah, didn't you say it could be A though?
We could have done something different in an earlier step, and then we could have finally driven down to that last line, but we would have required to have unpacked things a little differently up above.
Yep.
And then it wouldn't be A in there, it'd probably be C. No, we probably pull out C, well, I don't know what we do, but we'd have to do something different in an earlier stage in order to come up with what you suggested. What we can do, though, is this. EX, BX, and AB. Okay? My contention is, and what I've been trying to say is that these two rules, universal elimination and existential introduction, both of which we've used, that they're very intuitive. And I say so because it seems to me, if I know that every damn thing in the universe has the property B, then I could just pick out one of those things and say it has the property B. And on the other hand, if I know that that thing A has the property B, then I know that there exists at least one thing that has the property B. So those guys are no trouble whatsoever. And the way I want to spend the rest of our time today, right now, is by going over a few exercises where that's what's at stake. So I said there. Now, this one work on your own. What you're trying to do is to derive the thing on line 8, regardless of how many lines it takes you, from the thing up at the top. And in the problems we're working on this morning, as I recall, some do and some do not require that second column over there. I just got tired of trying to tailor the columns to the particular problems, and I put 3 columns on all the problems. So you may or may not need that subderivation line for any of the items we're going to work on right now. All right, Kevin, what's line 2? First of all, give me the line number, then the justification, and then tell me what I should put on line 2.
Using line 1 and a universal elimination, I got AA.
Okay, then go ahead, line 3.
Using line 1 and universal elimination, I got AB.
And then,
And then 2 and 3 with ampersand introduction, AA and AB.
okay? That's by the way, if you haven't noticed that in the Logic Cafe, that's a way that sort of cuts down on the number of times you have to type elaborate things or cut and paste elaborate things. If the conclusion is written somewhere, you can skip all those other lines and just go right down and write the introduction, cross out the question marks, and the Logic Cafe will accept that way of doing it. All right, any questions about this particular problem? Very, very straightforward, simple problem. But it does demonstrate the use of universal elimination in a very clear fashion. No questions. Good. Okay. Let me find my cursor. Okay, go to work on this one. All right, Michael, what would you do first on this one?
Line 1, elimination, I get CA.
And go ahead, next line.
Line 2 and elimination, I got not LA. 3, 4, and introduction.
I'm sorry, 3, 4, okay.
CA and not LA. And then 5, existential introduction.
Okay? Is that apparent? Okay, those are just two straightforward, non-difficult applications of those two new rules, and I have a good sense that you got them. So let's just do something a wee bit more complicated on this next one. This one, I'd like you to show that that is logically true. And it's long, so it isn't bolded, so it's a little hard to see, but I think you'll be able to detect it. Look at it very, very carefully. Look at it very, very carefully. And you might see that it's a little more, I'm noticing some people are having difficulty with it. Some folks, if you look at the bottom line, the thing that you're proved, look very, very carefully at it, and it should look familiar from earlier demonstration techniques that you've mastered. What's the main connective in the conclusion? Chris?
Application.
The horseshoe, correct. And how do you show the horseshoe sentences are logically true?
Assume the first part.
Assume the antecedent, see what happens. But that has to be done over there in the subderivation column, not the main derivation. So you're just saying, what if? You can't presume that you know this thing. That's what I was talking about before. If you have something in the derivation line, you can say, I know that this is true. So what happens if I know that's true? Then what follows from that? In the subderivation line, it's tentative. It's hypothetical. It says, well, what if this were true? What follows from it? And if you can ask, what if the antecedent were true? And if you can derive the consequent of a conditional, that means that you're entitled to move that back over into the main derivation line as a conditional. Nathan, let me know what you did at first.
Assume for all x, tx and not ux.
Because that's the antecedent of the thing that we're trying to derive from no premises whatsoever. What would you do now to line number 1?
Ampersand elimination for all x, tx.
So from line 1, what? What elimination?
The ampersand elimination.
You can't do that.
Can't do that?
Not from within because right now you've got a universally quantified statement.
Okay, then the universal elimination.
From universal elimination, then what would you choose?
TA and not UA.
Okay?
Then ampersand elimination on line 2. Give you TA.
Mm-hmm.
And then existential introduction gives you there exists a line for ty.
Correct?
And then using lines 1 through 4 with implication introduction, get the conclusion.
Okay, any questions about this one? No, I think I may have one more. Yep, there's one more. So go to work on that. Greg, what do you do on line number 2?
I did ampersand elimination on line 1 to get universal XAX.
I'm sorry, to get what?
Universal XAX.
Okay.
And then I did, on that, on line 2, I did universal elimination elimination to get big A, little a. Then I did ampersand elimination on line 1 again to get universal X, not BX.
That's ampersand.
Yeah, yeah, sorry. And then universal elimination on that to get not B, little a.
And you're entitled, since this is universal, you're entitled to use the same letter you did before. You would not be entitled, if you were following a universal elimination, to then follow with an existential elimination, which you won't get to later. You can't just automatically say you use the same name, because you can't know that. Go ahead.
Then I'll use ampersand introduction on 3 and 5 to get big A, little a, and not B, little a.
Okay.
And then you can use an existential introduction on 6 to get.
Right, because if you know all of these things are this way, you know that there's exists at least one, so you're entitled to go in that direction. If you have a universally quantified set of sentences, you can then move quickly and simply to that. All right, any questions at all about these first rules?
I have a question
Eric.
about this one.
Yeah.
Do you need to break it apart with ampersand elimination to remove the universal quantifier?
Do you have to do which?
Do you have to break up the and
Yes.
to remove the universal?
Right.
You
As
have
a
to.
yes. As a matter of fact, you will find that you could also go to you could there's ways of getting to, you can conclude this. I forget all the rest of this stuff. You can conclude this too. But we don't have that equipment yet. Okay? If you know all x ax and all x not bx, you know all x, both of those things. But you can't do that now. And what they want you to do is always operate on the main connector. That's the whole focus of the Logic Cafe is to make the strategy simple and straightforward and reasonable. So you always work on the main logical function. If it's a connective, if that's the main function in the thing, work on that. If it's a quantifier outside of everything, work on that. You can't work on, Nathan wanted to work on using an inference rule in the middle of a quantifying sentence. You can't do that. You can use the replacement rules, the ones that go, like if it were a disjunction and you've had AA or BA or something like that, or even within a quantifier, AX or BX, you can swap those around because that's the replacement rule. Those things are equivalent even in the middle of formulas. But you can't use the inference rules that way. You only operate on the main logical connection of any proposition. We have covered the first two of these new rules of inference, and what I want to say now is a few words about the second two, which are more complicated and will cause you more trouble. They cause you more trouble just because they have sort of odd nuances. I think that they're intuitive all right once you finally get straight what we're doing, but it may take you a little while to sort of get comfortable with them. All right, now the first one is universal introduction. And it's easy to say what it allows you to do, but then the conditions down here are what might be problematic. So you have a sentence that has one of our names in it, any one of the lowercase letters up through U, then you're allowed, if under certain circumstances now, you're allowed to say that's true of everything in the domain of discourse. Now that seems weird. I mean, we have one example. Why should we be allowed to conclude that it's true of everything? Well, this is allowed only in cases cases where the name is arbitrary. What does that mean? Well, the A will be not in one of the top lines of the derivation. It won't be in a premise. Okay? Because there it appears as a name. But if it doesn't occur in any premise, or over here on one of those right columns in any one of the undischarged subderivations, and by what does it mean when I say an undischarged subderivation? One that you're not finished with yet. You can't pull things over from the subderivations except for the last line or the particular conclusion is justified. Like when you're doing not elimination, the only thing you're allowed to pull back into the main derivation column, what did I say, not elimination, is the opposite of the thing you assumed in the first place. And the same is true for not introduction. Both of those rules allow, the only thing you can bring back over into the main derivation line is a particular thing that the rule entitles, that the rule licenses. So you can't be bringing things over that are in a subderivation that aren't the things that are entitled. Okay? You may, in some cases, bring over an A, but those are very special cases, and I think we may cover one of them this morning if I get to it. But in any case, you can, in some cases, for example, using the rule of what is it? I can't remember the name of the rule, but the rule where you either one of the curl introduction or curl elimination, either one of those rules, if what you assumed in the first place had an A in it, a name in it, rather than a variable, and if you're able from that assumption to derive a contradiction, you're able to bring the negation of that thing with the name in it back into the subderivation line. But that means that you've discharged the assumption. So A can't occur in any premise, and A can't occur in any undischarged assumption, and it can't occur in the thing you're concluding, because you have to eliminate all those A's. I mean, if you're going to move from a sentence that contains a name to a universally quantified sentence, you have to eliminate all the instances of that letter, of that name in the sentence. So that's a mouthful. And this is the summary of it. Universal introduction is allowed when you have a name in a formula, in a sentence, and you are allowed, and if it's arbitrary in that sense, you're allowed to derive from it the universally quantified sentence that replaces that name with a variable. Now, having said all that, it might be useful to take an example. And I'll use one that comes from the Logic Cafe. And first of all, here is an argument. And Halpin calls it the IRS argument. And it's a fairly standard sort of thing. It says if you make more than $4,000, then you must file. And they're not talking about you. They're talking about if anybody in the domain, the universe of discourse, anybody who's a U.S. citizen and over the age of such and such, and whatever it is, that's the domain of discourse. If one, you might well say, makes more than $4,000, then one must file. Furthermore, and if you're required to file, and that's what that says, you must file, you're required to file. If you are required to file but don't, then you'll be prosecuted. And so the conclusion is, if you make more than $4,000 yet you don't file, you'll be prosecuted. Now, the way we're going to symbolize that argument is like that. For all x, if x makes more than $4,000, and then remember, the universe of discourse doesn't include Shamu anymore, nor does it include the general Sherman tree. If this is the universe of discourse, it's U.S. taxpayers. If x makes more than $4,000, then x is required to file. And the second sentence, the second premise in that argument was, for all x, if x is required to file, and X doesn't file, it's not fx, then X will be prosecuted. And the conclusion is supposed to be, for all X, if X makes more than 4,000 and doesn't file tax forms, then X will be prosecuted. That's the way the argument's supposed to go. So the question here is, the reason why we're bringing this up is, well, how would you prove that? How would you derive that? How would you use our techniques to draw that conclusion? So what I want to do is to illustrate that. So what I want right now, once again, this is an illustration, so we'll work through this together. Each time we're told what we're supposed to do, and I want to get from you some, how we're going to apply these rules. So if I use all, this is not the if I use all elimination, or universal elimination on line 1, then I come up, this is simple, mx, or ma, horseshoe ra. And if I use the same thing on line 2, I'm going to use the same variable. I don't have to, but it's going to be what I need to do. On line 2, I'm going to get ra ampersand not fa horseshoe pa. And a reason for choosing the same variable is we're trying to come out with we're trying to conjoin two things that are not conjoined in the premises. We're trying to get those things together in our conclusion, if you look down there. Now, line 5, it suggests that we assume something. And another thing we can look at, we go all the way down to line 12, remember, this is supposed to be an illustration of universal introduction. So what we probably should think of is what we want down here is MA and not, MA and not FA horseshoe PA. I mean, do you see why? What we're going to try and do in the very last line is use universal introduction. And so we need to have something that has, we need to have a sentence that has a name in it for which we will substitute a variable and universally quantify. So if that's what I want to get in line 11, what should I assume in line 5?
MA and not
And since what I want finally to get is PA, what I'm looking for is wanting to use 4, which sort of pulls PA out of that. So from 5 by ampersand elimination, I'll get MA. And from 5 by ampersand elimination again, I'll get not FA. And from 3 and 6 by OR elimination, I'll get RA. And 7 and 8 by ampersand, I'll get, do I want 7 and 8? I want 6 and 8, yeah. No, that's not right. No, I do want that. I want RA and curl FA from 6 and, 7 and 8. And then that gives me, by OR elimination 4 and 9, I get PA, which allows me then, from 5 through 10 by horseshoe introduction, I get line 11. And then finally, from a line 11, by universal instantiation, I get that. Now, why am I entitled to do that? Because, first of all, there's nothing, I've discharged all this stuff over here in the subderivation, but there's nothing particular that I've assumed about A, because I start out with universal quantifiers. It says that these first two premises are true of everything in the universe of discourse. And so I say, all right, well, let's just choose as an example, an arbitrary example, A. And then using those, I'm able to come up with line 11 using our normal techniques. And then I say, all right, well, remember, it was just an arbitrary assumption that I chose A. There's nothing special about it. I've not said something, we don't know what A is. It could be any citizen, still any citizen. This is an arbitrarily chosen name, I may now universally quantify over that.
So it's only allowable if every single predicate is already in the universal qualification in the previous line.
Every single predicate, every use of A has to, you have to follow this through, watch for the instances of A. As long as you're not assuming anything special about that, as long as it's still just one of the things in the universal discourse, and there's nothing special said about it, you're not bringing in other predicates that say something special about it, if it's still holding on to its arbitrariness in the sense that you're just saying, take any one of those things in the universal discourse. The premises say the following is true of all of them. If you've got something that's existentially quantified, you can't use an existential quantifier and then choose a letter that you've been thinking of as arbitrary. Existential quantifiers say special things about special things.
If you just had a line that had like P of A,
Where?
it was a
In the
premise-
derivation
in the
itself.
premise.
Yeah, let's say if it's in the premise.
Yeah.
And you
premise.
can't use then A. There's nothing arbitrary about A. You can't use A anymore if it's in a premise, and that's why this clause, right?
Okay. Oh.
Any questions? All right. All of this will be much clearer as you work through the Logic Cafe, because again, it's much more difficult to sort of simply explain this stuff and have you comprehend. It's more difficult to sort of wrap your head around it in that way than it is to just sort of in practice work with those problems in the Logic Cafe.
Doesn't A occur in that discharge assumption?
Well, we've discharged it. We've discharged it. As of line 11, we've discharged this thing. And we are entitled to bring out the implication that's listed here. Because all this says is, well, if, in other words, just pick out an arbitrary member of the universal discourse and let that be our example, because we need to work with something. We've got to get rid of those quantifiers so we can work with this stuff. Let's choose A, and we find out that, well, if we choose A, then, and we could have, we're directly allowed to draw out 3 and 4 from our premises. This is just an indirect way of drawing out another consequence from 2 premises. It's an indirect proof. You say, well, let's say let's say MA and not FA. What follows from that? That's all. That's the only question we're asking. What we show is that what follows from that is PA. So if A is our example of something for which it's true that MA and not FA, it follows that PA. Other questions? Okay. Now, that's not good. This one is yet more complicated. So let's do that. Existential elimination is really quite counterintuitive. It's hard for you even to write it up on the board. You'll get a nicer formulation in graphic form in the Logic Cafe. But let me see if I can explain what's going on here. Let's say among our premises, or let's say any point in an argument, in a derivation, we have an existentially quantified statement. And the existentially quantified statement needs to be the whole line. The whole thing has to be existentially quantified, not just part of it. If we have a line like that, in this case, EX, PX, and it could be any as complicated a sentence as you please, any sentence in predicate logic. And we want to prove just anything at all. I mean, let's say our objective is Q here, all right? We're entitled to do this. Take, it's just sort of as a, it's sort of the illustration. We don't know what the X is of which this is true. But this sentence tells us that there's something of which it's true. there's some x such that this. Okay, let's just sort of say, we'll just give it a name, an arbitrary name. We're not talking about anybody in particular. You know, we're not going to talk, once again, not about Shamu, not about Queen Elizabeth, nobody. We're just going to say, okay, let's just give it a name so we can work with it and see what happens. So we just take the same sentence and we substitute A for all the x's in it. Okay, and we can only do that one step at a time. So if there's many quantifiers here, we can only do the outside quantifier. We're assuming in this case that the outside quantifier is the existential quantifier. So, all right, so let's just, give it a name, just for illustrative purposes. Call it A. And then I didn't know how to write this without, sort of expanding a lot of space that I didn't want to use up. Then in some number of lines, n minus 1, we run a proof, a derivation over here, sort of standard techniques, through n minus 1 lines. We get down here, and we establish on line n, okay, the next line, we establish something q. If this premise allows us to go down to q, we can pull q out. Because this says that p is true of something. It says, all right, let's give it a name. If it's true of something, it doesn't matter what thing it is. If it's true of a thing, then we can establish some other proposition q. Well, this said that it was true of a thing. And if we're able to derive q from from an illustrative example, then we can pull q out of here. And the way we write that is it comes from 1 and 2 through n by existential elimination. I think this provides the idea of illustrative. This is the qualification. I didn't have enough room on the other slide to put both together. It would have been nice, but in this particular slide, this shows you what the qualification is. I'm allowed to do that if A doesn't occur in any undischarged assumption, again, undischarged assumption. A doesn't occur in the premises, and it doesn't occur in the thing that I'm concluding. In order to come back out of this, I have to have something that is free of the arbitrarily chosen name that I've been using for my illustration. Again, that's a lot of words. Let me see if we can work through an illustration. All right, in line, what I want to do, now to discharge it, let me show you how this works. I want to operate on the existentially quantified premise number 1. Because after all, what we're trying to illustrate right here is this rule of existential elimination. So I will assume that CA and PA, which is a substitution instance of number 1. It says that something exists such that CX and PX. What you missing?
Gotta switch a battery.
Thank you. All right, so premise number 1 says that it's true of something, that it's C and P. And so we're just going to say, let's just call that A for now. All right, by 3 by ampersand elimination, I'm going to get, I'll use PA. From 2 by universal, I should use CAS. From 2 by universal elimination, I can choose anything I want now. I can choose A because it says it's true of everything, line 2. So it's also true of A. So I can use that same variable there. I can always use universal, I can choose the same variable when I'm using universal elimination on top of, after existential elimination, but I can't do the other way around. So CA horseshoe IA And then from 4 and 5 by horseshoe elimination, I get IA. And from 3 by ampersand elimination, I get the other part, the PA. And then finally from 6 and 7, I get IA and PA. And still over here in the subderivation problem area, I'm entitled, because this has been an arbitrary thing, in this column, I'm entitled to come back out of the choice of A as my name. I'm entitled to say exists in X such that IX and PX, because if you think about it, that's what it says. I mean, my assumption here, I mean, if CA and PA were true, then there exists an X such that IX and PX. And since number 3 is simply an arbitrarily chosen example from number 1, which also says that there's something exists such that CX and PX, since that's it's just sort of an arbitrarily chosen name that we're going to work with, since something has these qualities, then let's call it A. I'm now finally allowed in line 10 to go 1, 3 through 9 by existential elimination. And the existential quantifier I've eliminated, and this is the thing that's counterintuitive, is the one that appears in the premise, in line 1. That's why 1 appears in the justification. What I've done is I've sort of eliminated the existential quantifier in premise number 1, in line 1, and I did that I began doing that at 3. I was able to show that if I did it, I could have chosen any arbitrary name, but when I came out of that, I reintroduced an existential quantifier for the bottom line and pulled that out. I could have pulled out anything along that way. All right. Now, once again, this is going to be a lot simpler as you work with it, and because once the Logic Cafe will ease you in. I'm sort of leaping forward to give you sort of a preparation for the sorts of things that you're going to be working through in the Logic Cafe in the first 2 tutorials of Chapter 8. That's all we're working with, not tutorials 3 and 4. Just the first 2 this week. And these are the sorts of things you'll be introduced to. And what I'd like to try for a few minutes doing is at least 1, perhaps 2 problems. We'll see how long this takes. So at this point, go ahead and start working. The objective is to derive the thing in the title box. All y exists x, lxy. In other words, while in this particular case, because there's no conjunctions, no disjunctions, or anything like that, you can't switch these things around. You can derive them. See what happens by trying some of our tricks. I mean, you have to work from the outside in, so the first thing you need to do is to sort of try an existential elimination. Let me do this one. We're going to assume on line 2 that for all y, LAY. Once again, I don't know anything about A. That's the reason I can bring it up in the subderivation. I can't conclude anything about A, B, C, D, or any other particular name, because all I have in my premise, all I have is that there is something such that it's what? Let's call that larger than. It's larger than everything. And that's all the line. It says there's something. I don't know what it is. It could be, Shamu for all I know. So we're just right now we're going to presume that we're going to just give it a name, call it A. So it's just an illustration. It's that one of those things, if there are more than one of those things that are larger than everything. Okay. Now, from line 2, I could use universal elimination and get, I'll choose B, LAB. And now I want to work back out. I know that there exists an x such that Lxy from the premise. So next thing I want, obviously, is since I'm working toward all y ex, I have to work from the inside out going backwards. I want that. L x b. And so that's obviously going to be a case of existential introduction. I'm entitled to do that because the A was chosen completely arbitrarily. All right? Now I could either bring that back in right now, or I can stay out there and do the universal. So this is from line 3. For by universal introduction, I can go all y ex Lxy. And now from 1, 2 through 5 by EE, once again I'm eliminating this existential quantifier. I can just pull this over. I just bring the same thing over. I told you that these rules are somewhat counterintuitive at first. What you need to do is to work through the problems in the Logic Cafe, and work through the tutorials. If you're having trouble, read the tutorials carefully, and then if you have trouble with the particular problems, keep working on them until you find yourself satisfied. I mean, you should find yourself satisfied after a little while. Oh, I get it now. I see it now. If that doesn't happen, then that's what the conversations in my courses are about. We're supposed to try and study together, work together, act together. You haven't been using that facility, but you should be.
So in step 5, hasn't B only been used in undischarged assumption?
But I'm still, in step number 5, I'm still in the subderivation.
So that rule about not being able to use stuff is in an undischarged
Oh, I can't, in a derivation, I can't use something that's to the right of the column I'm working in. I mean, let's say I had another, because this is just being assumed for a second, okay? And then we're seeing, well, what happens? It's just like, as always, it's just saying, if that were true, then what may I conclude? Well, if that were true, I can conclude this. But this was just a name. We know that it's true of something. So once I've gotten rid of this something that I sort of assumed arbitrarily out here, once I've gotten rid of the reference to A, then I can pull it back out. But I can't pull it out if I've just arbitrarily assumed it. I can't bring that out here. Because remember, this says that there is something like that has this property. So I don't know what it is, but let's just give it a name A, so I can get rid of that existential quantifier for a second and see what happens if I just give it a name.
So when you use a universal introduction, it's really not very different than an existential introduction. There's not really any other limitations on it.
The universal introduction is limited. I'll remind you what those are, but that too has to do with. Oh, where am I? These are the universal introduction. These are the qualifications on that one. And once again, it's referring, when it talks about these undischarged assumptions, it's saying, now this is a discharged assumption. I've assumed this up here. I've gotten to this, and then I've closed it out. I said I'm entitled to conclude this in this line here in the main derivation. And so I've now discharged, closed off, finished the work that I was doing with that assumption. So this is discharged. I mean, I can't, and over here, what appears here, and that's one of the reasons why I think help and set this thing up. This stuff, until you get to the bottom line, is what he calls undischarged. Once again, though, work with it. Not working with it will just leave everything vague and unintuitive. and keep working until it is intuitive. Any other questions? Okay, I'm off for Montreal.